Okay, we're going to talk about electronegativity. And first of all, electronegativity is very important in organic molecules. It is the difference in electronegativity between two atoms in a bond that is the cause of much reactivity. So let's look at this and see what a difference in electronegativity will cause. The first thing we're going to look at is this simple molecule of hydrogen chloride. And you can see down here that hydrogen has a Z-effective of 1 and chlorine a Z-effective of 7. Now, I'm not going to go into where this comes from, but basically it's saying what the effective charge on the nucleus is. So chlorine has a much higher effective charge on the nucleus than hydrogen. As a result, these bonding electrons are drawn closer to chlorine than to hydrogen, not to be symmetrical like this, but instead to be shifted over to the chlorine. When you shift the electron cloud over there, that causes negative charge to be drawn toward the chlorine and away from the hydrogen. This causes slight positive charge to develop on the hydrogen and a slight negative charge to develop on the chlorine. It's not a full positive or a full negative, it's slight. So if I want to indicate this, I do this with this del positive and del negative that we have here. The Greek letter D, the lowercase Greek letter D is called delta, and it means small, partial in mathematics. And so when we write del positive, it means partial positive. Del negative means partial negative. And this we call a dipole, two ends. Dipole stands for two ends. So this bond has a positive end and a negative end. But remember, it's not full positive or full negative. And we call that del positive and del negative. The electronegativity difference also can be written with a vector like this. It's not so common in organic as the del notation, but it can be used. Ignore the page number. That's from the 1201 book that was used a while back. The electronegativity that you do need to know is this trend in the periodic table, which is as you go up and over, electronegativity increases. However, recall that the noble gases do not enter into bonds, so they do not have any electronegativity. This means that the atom with the greatest amount of electronegativity is fluorine. So the atoms that are closest to fluorine have the greatest electronegativity. The farther it is away from fluorine, the lower the electronegativity. The only other trend that you need to know about electronegativity is that hydrogen has less electronegativity than any of the nonmetals except for phosphorus, which it has the same electronegativity value. So that means when hydrogen gets into a bond with any of the nonmetals, carbon, oxygen, or nitrogen, there's a small to large del positive on the hydrogen and a del negative on the other atom. Now, when we talk about carbon-hydrogen bonds, the electronegativity difference is there, but it's relatively small. But there's another thing that goes into play with that, and that is when you have carbon-hydrogen bonds, you usually have a lot of symmetry around that carbon, and that negates the ability for electronegativity to be of any significance. Symmetry is very, very important. Okay, we call a dipole charge separation. If the charge separation is great enough, we have an ionic bond. If it's not there at all, then we have a nonpolar covalent bond. And when we have a small del positive, or even a large one, when we have del positive, del negative, and not a full positive and a full negative, then we have what's called a covalent bond. So this really is a continuum. You don't really have pure ionic or pure covalent except with two atoms that are identical in a symmetrical molecule, you will have a nonpolar covalent bond there. Okay, so to practice this, now what I'd like you to do is pause the lecture and go ahead and draw in your del positive, del negative dipoles on these molecules so that you can verify that you understand this, and then restart the lecture. Okay, well, if we look at this, these molecules all will have dipoles. Well, not all of them, but most of them have dipoles. The carbon-hydrogen bond here has a del positive on the hydrogen, del negative on the carbon. The carbon-nitrogen bond has a del positive on the carbon and a del negative on the nitrogen. So this means that the carbon in the center is both del positive and del negative. So we look at the molecule overall and see del positive on the hydrogen and del negative on the nitrogen. If we go down here to the sulfur dioxide molecule, you will find a del negative on either oxygen and a del positive on the sulfur. Nitrogen and chlorine actually have the same electronegativity, so this bond is nonpolar covalent. If I look at hypochlorous acid up here, the hydrogen has a del positive, oxygen del negative, and chlorine del positive. Chlorine has an electronegativity of 3.0. Oxygen has an electronegativity of 3.5. That you would have to look up. It's not something I expect you to know. Hydrogen del positive, oxygen del negative, and hydrogen peroxide. The oxygen-oxygen bond, of course, is nonpolar covalent, and then hydrogen del positive, oxygen del negative. And then down here on carbon dioxide, the oxygen is del negative, carbon del positive, and the oxygen del negative.